Gammas reflect the change in delta. So you can think of a gamma as a slope of the delta curve. Again, we'll identify 40 as the strike. And if we go back, I note here, and this again comes from put-call parity, I'll make this clear in a minute, that gammas for puts and calls are the same. And this comes directly from put-call parity. So we can look at the slopes of the delta curves and see the shape of these curves. Namely, that if you go back to the delta curves, the slope of, let's say we look at the 3-month option, the slope is nearly 0, way out of the way in the money, way out of the money. And it's maximum in the middle. And that's what we see here. We see that the slope is 0, way in the money, its slope is 0, way out of the money, and the slope of the delta curve is maximum around the strike price. You can do the same with the long-dated option. If we look at the 3-year option, it looks like the slope is maximum right around here, a strike of 30. And it gets close to 0 to the right, but it doesn't get close to 0 to the left yet. And we look at that 3-year option, which is here. This is the 3-year. We can see that the slope gets close to 0. It maximizes around 30. So again, you can go back to back that the properties of the gamma graph can be understood in terms of the shape of the delta graphs. Next, if we look at call option vegas, so this is the sensitivity. And so notice the units of this. This is 20 cents. So let's do an example. So this is saying that if the stock price, this is again, it's a strike of 40. If the stock price is at 40, let's look at the 40. It's saying that if I have a 3-month option, it has a vega of around 7 cents. If I have a 1-year option, it has a vega of, let's call it 14 cents. And if I have a 3-year option, it has a vega of, let's call it 20 cents. Now, this means that if the volatility goes from 30% to 31%, a 1% increase in volatility, that the price changes by 7 cents, 14 cents, or 20 cents. So this is the vega per 1%, which is why this is equal to 1 over 100 times the derivative. Because in general, what one would do is to multiply the derivative of the option times the change in sigma. Well, sigma is a decimal. Going from 30 to 31 would be going from 0.3 to 0.31. So this measure of vega takes this number, it takes the derivative and divides by 100, and then it multiplies delta sigma by 100, so it's now in decimal units. So instead of going from 0.3 to 0.31, which is what we would use for delta sigma, it goes from 30 to 31. So you just see the hundreds cancel out. And this is the same convention used for rho and psi. The numerical units of vega are not actually the derivatives. The derivatives are 100 times bigger than this. The derivative of this would be 20. The derivative of this would be 14 and 7. Okay, so it's important you understand this convention for the purposes of working on problems. So in terms of the shape, besides the convention, again, you can see that in general, vegas tend to be maximum around the strike price. When the stock gets more into the money or out of the money, the sensitivity to changes in volatility are less. And the reason is it's logical that if you're in the money, more volatility keeps you in the money. If you're out of the money, it keeps you out of the money. It's really when you're near at the money that an increase in volatility can change the balance more materially between whether you get a payoff or not. So you get a bigger price effect. Not that material, but in general, a bigger one.